pessoal, a apresentação vai ser em inglês, mas se vocês quiserem perguntar em português, eu posso traduzir a pergunta para o nosso apresentador. E ele falou que não se importa que as perguntas sejam feitas durante a apresentação. Eu vou também colocar um link aqui dos slides dele. Coloquei aqui no bate-papo, onde vocês podem baixar os slides para ir acompanhando no seu próprio computador. Okay, so it's very nice that you can give us this talk today, Stefanos.
Yeah.
Stefanos is you're a postdoc, right?
Senior researcher.
Senior researcher, yes, at the University of Zurich. And you do understand that you work in this analysis that got this nice publication in Nature Physics. And it's about double particle scattering and the 3D structure of the proton. And we are very happy to have you here. So
thank you. Thank you for inviting me to give this. I really like to talk about this subject. And since I don't know the background, I have like one slide or two just to introduce the whole process. And I start with this picture on the left, which shows a molecule. This is to be exact. This is an adrenaline molecule. And I remember when I was in very early grades of school that we used this Play-Doh and toothpicks that we would make, water molecules and stuff. And later on, as you progressed in school, you learn that this is not a picture. There's more things inside, and they give you this picture of the electrons going around. There's something positively charged in the center that attracts the electrons, and then you zoom in the nucleus, and you see that there are neutrons and protons, and then at the moment that you enter university, or at least when I entered the university, or a bit before, I learned that, the protons is not the most fundamental part. There are constituents inside the protons and the neutrons and hadrons, and these are the quarks. And then later on in the early stages of the university, you hear about the gluons and the strong force. And then you also are introduced in other concepts that were new to me at the time, that you have the C quarks apart from the valence quarks. And not only that, but we also know with relatively good accuracy how much momentum these partons are carrying inside the moving proton, and we can separate them, and we can see what this value is for the up, for the strange, for the U, for the down, for the gluons, and etc. And these are known with relatively good precision, and this is illustrated by the bands here. So we have a good understanding of a single parton distribution functions inside the proton. Of course, not in very low X, but in principle, we have a good understanding. And also at that time, we were being introduced in the Lorentz vectors and how one would do some easy interactions. For example, such a diagram, if we consider only the black lines, it would be like two incoming particles, two outgoing. And then if you would move on, and at least for me that I chose particle physics in the university, they would say, oh, look, this could be, I don't know, something like gluon, TT bar, and then T can decay. And this is, of course, the B, the W, and then two leptons or two quarks. It's your choice. And in principle, when I started doing my bachelor thesis, when I was analyzing Atlas data at the time, using simulations, how these interactions are modeled, I had this naive picture when I started. And then looking on the modeling, in fact, it looks something like this. So you have this part here. That is, you can see my mouse, I assume.
Yes, yes.
Okay, cool, excellent, thank you. So you have this this piece, which is like the proton, and you have another proton coming from the other direction in Z. And you have the hard scatter, as we say, the one that carries the most momentum. And here you have the, let's say, the two gluon fused together. And these can give the final state particles. So the process here from this Sherpa cartoon is gluon Higgs. So you have like the two gluons, and then you have TT bar and the Higgs, and then the Higgs goes to BB, and then you have the same decay of the top as before on the previous slide. And then, but this is not only the picture, right? Because at the end of this decay, you have the hadronization, which one spends quite some time in order to model it. But there are other stuff that are going around at the same time in this interaction. What you have are, of course, the beam remnants, so like the quarks that are not, or the quarks or the gluons or the partons that do not interact. And you have all these, inside quotes, noise under it. And since I really like noise, I was like, sounds very interesting. So this can be described as multi-parton interactions. And it is, in a sense, when you have more than one partons from one proton interacting at the same time, and can give rise to a variety of processes. And this is not news. This has been around 45 years now. No, I'm very bad at math. Yeah, around 45 years. So this was postulated first in this paper in 1979. Many would recognize this name, Halzen, if you have the black book of quarks and leptons in the university. Halzen is one of the authors. So Halzen with colleagues described this process like the multi-parton interactions, and they say that what you can have is that instead of having this interaction where you have partons and then the production of hadronic, you can also have, which is called single parton interaction, because you have one single parton interacting. What you can have is more than one partons from one proton and more than one parton from the other proton interacting and giving you the same final state, so two gammas. Interestingly enough, from all these measurements that we have up to now, this one was never studied up to now. So NPS, in principle, so like double parton scattering, triple parton scattering, quadruple parton scattering, are very important for fundamental studies. As we saw recently, LHCb came up with the discovery of the tetraquark, and this tetraquark was in the decay mode of the 2J size, and one of the major backgrounds in order to understand if there is more than one resonances and how this background is under it, it was the single and double parton scattering of the 2J size. And not only that, but it's also very important as an input on the Monte Carlo generators, because currently it's not modeled super accurately unless you pay a lot of attention to it. And in principle, the double parton scattering goes through these cartoons, so you have like two interacting partons again, giving you two final state objects. So this is the most simplistic picture, and one could sort of relate it as a function of the single parton scattering as lambda square over q square. So you put in the q square your favorite process, your favorite particle, and then you can see how important it is. And considering the channels, the die J size, since J size is relatively light, is the double parton scattering becomes important. But if you go to other processes, other particles like W's and Z's, this becomes less. But still, it's quite interesting to study, and it is in there in our data set now. And looking on the theoretical calculations, you can see that we are reaching now the area where the double parton scattering, for example, in the CC bar production, it will become as important, as abundant as the pure CC bar. So it's something that we have to put a lot of effort, I think, to now understand what's going on. And indeed, since quite some time, we have many experiments that are using many final states in many different square root of S's and give results. And one summary of these results is in this plot here on the top right, where you see mainly these are experiments in central rapidity. That's why you don't see LHCb there. You have from UA2 to Fermilab and then to LHC a lot of measurements, quarkonia and electroweak bosons, jets, photons, hard objects, a variety of ingredients. And if one wants to, let's say, go back to the picture that, okay, I know I have a Lorentz vector, another one, I can calculate the amplitude, I can calculate the cross-section in the single Parton scattering case. In the double Parton scattering, to do the equivalent is not as straightforward because you have a complicated formula like this. So, and inside here, there are some things that are still not super clear from the experimental side of view. So these are, for example, the Y position, the position of the parton in the transverse plane, how the two partons are correlated with each other, the color, the spin, and of course the double parton density function, which we also don't have a good hold of it. So what we usually do, since we are on the experiment side, and what we usually do is that we say, okay, we sort of close our eyes, we ignore all these correlations, and we hide everything under this parameter that's called sigma effective. And sigma effective can be derived purely geometrically if you just calculate the protons and how much they would overlap. And this will give you an answer of around 30 millibarns, which was initially used in simulations. From the experiment side, what we see, if you look on this picture, is that you see a lot of measurements involving quarkonia, so these are the blue and the red, in the lower side, between 0 and 10 millibarn, and then the black points, which use the harder objects like photons, jets, electroweak bosons, being in the window between 10 and 20 millibarns. So there is a distinct difference between what particle you're going to use in your final state. And this difference shows exactly this hide under the carpet that I was talking before. This shows that lighter particles that are mostly gluon-induced, like WJ psi, so the initial particles that you're fishing out from the protons are gluons, will have smaller effective cross-section with respect to harder objects like quarks and jets, which are initiated by quarks. So this simplicity hides this effect, having two different, ignoring the correlations of the partons. And now, if you move to one step further, and what we have done very recently, the paper is to appear in the journal, hopefully within this month, is to move and look for it for double Parton scattering in PA, and to be specific P-LED in CMS. And the P-LED case is at the same time more interesting and more noisy. So the noise comes from the fact that when you try to think of what sort of DPS you have, you end up with two different configurations. You have here your projectile, so this small blue is the proton, and this, of course, we need two different partons from the proton. And now, if I'm going to look for two different partons, two partons from the nucleus, these can come either from one proton or it can come from two protons. So in the double Parton scattering case, you have to take into account two different sources of double Parton scattering. And of course, one is let's inside quotes trivial because it's the same case as in the PP collisions. But in the other case, you can you can do some math, and you can calculate how much is the effect of this effective cross section. And in the end, it gives you a number that in principle in P-LED, the double Parton scattering is enhanced by a factor of 600. So it's although the luminosity that we collect is very low, it's a DPS enriched, let's say, sample, and it's good to look for it. And what we have looked for in CMS is double J psi, and the three modes now that you can have double J psi in the P-lead interactions is first the SPS, where you have, as I said before, is mostly gluon induced. So you have the two gluons giving you the two J psis, or you can have two gluons interacting with two gluons from the same proton, or you can have two gluons interacting with two gluons from two different protons. So this is DPS1 and DPS2. So in order to have and to be able to see this decay mode, we really scraped every single statistic. We went as low as possibly in the kinematic selections. I'm not going to go through to the details, but for those that have done analysis before, for the muon case in CMS, you can appreciate that 1.3 GeV is to the bare lowest level, to the lowest level we can really get anything sensible out of CMS and muons. And this is reflected in the available statistics. So here on the top right, you see the two J psi distributions. So since you have two J psis, there are two different peaks. And the signal component is not the black, but it's the red curve here, because we have also the case that we have a true J psi and just background here. That's why the first J psi, which is the most energetic one, is more signal-like, and then the second is a bit more noisy. And since with this we were really just below the observation limit, then we just pushed the effort to include the electrons. Although in this low PT regime, electrons are very, very tough. You can see here the resolution is a lot worse with respect to the muon case, but still there were a handful of events. We measured 6 ± 4, and the very small significance on 2.3 in combination with the 4.9 pushed us to the significance of 5 sigma. So we were very happy to declare the observation of this decay of this process. But this is again SPS, DPS1 and DPS2 all together. So the first thing that we can do is calculate the cross-section, and the formula for the cross-section is relatively straightforward. You have the number of your signal events, and then you just need to correct for the efficiency, the integrated luminosity, and the branching fraction of the two J psis. And for this, for calculating the cross-section, we used only the dimuon case, so just one decay mode. I just have here the numbers just for complicity, just someone wants to see. In the end, the cross section is 22 ± 9 with, of course, this statistically dominated measurement with a 1.5 systematic where we do a good job. And this is where the fun part starts, because now we will aim to see what's going on with respect to the SPS and DPS, and try to extract for the first time the effective cross-section in the PA system. And in order to do that, you need to go and look on which variables are good in order to discriminate the single part scattering and the double part scattering. And this one is the delta phi and delta y. Historically, these were since the first, at least the first days of the first analysis came from Fermilab and LHC. These were the two variables that were used, and these are the variables you can see on the right. So on the top you have the delta phi, the difference in the azimuthal angle, and the delta y, which is the difference in the rapidity. And in principle, what you would expect if they were ignoring our physics, if you have like two incoming particles and then two outgoing particles, what you would expect is that if there was a single parton scattering, like two particles will give you both particles, final state particles, then these would be back to back. So you would expect a very sharp peak at delta phi equals pi. And what you would expect from the double parton scattering would be just something very, very democratic, like flat. because there are two uncorrelated, in some degree, partons from one proton and two uncorrelated partons from the other side. But in the case of the J side, this is not the case, because in the delta in the SPS you don't have the system where these are produced back to back, but you have all these complicated diagrams that you see below. That most of them will give you it will be more probable to give you collinear production rather than back to back. So what we did is that we went to the delta Y, so the only the difference in the rapidity, where we observed that from the theory and a data-driven sample, we saw that above the third bin, the sample was purely DPS, and the DPS sample we generated by taking the signal events and just doing event combinatorics. So we were taking literally J size from one event and J size from the other events that really didn't know anything about one another. So it was like a very pure DPS sample. So we did this, and we fitted the distribution in this DPS pure region, and from this fit, we extracted how many DPS events we were expecting and how many SPS events we were expecting. And we also projected that in the plot above to see how it looks like. And you can see that in all bins we have a very good agreement, although the statistics are very small. Unfortunately, the DPS yield was very small and had a large uncertainty, because this is a tricky business to fit. Doing the math and plugging all the right numbers in the cross sections, and again here we use the pocket formula, so the effective cross section will be given as a function of the double parton scattering cross section that we measure, and the single parton scattering of single J psi that we take from Helaconia. We were able to put a lower limit on the effective cross section. So the result here looks like that in comparison with the other measurements. Again, this is a gluon induced, so we were expecting to go low as a value of sigma effective, and in the end we were like, I mean, this is unfortunately this is the only P-lead sample that we have in the LHC, and unfortunately we are not going to have any other P-lead runs in the near future, at least up until the start of HLLHC. So up to now, what we can say is that we derived a lower limit on the di-J psi final state using P-lead. And now I'm going to shift gears and go to a higher order of parton scatterings. And these were based on recent ideas. The first papers appeared in 2017. This is from David and Huasheng. They are both, David is a collaborator in CMS, Huasheng is a theorist. That said that one needs to have a go on the triple parton scattering. There might be events in our data set, and in principle, David in this paper went and calculated the correlation between the effective cross-section of TPS and the effective cross-section of DPS, again using a pure geometric model. And then Huasheng cranked some numbers and reported that in the case of the triple prompt J psi, the double parton scattering and the triple parton scattering are the dominant process. So this is like a golden channel to study double parton scattering, triple parton scattering. So, okay, yeah, I mean, let's do it. Let's see what we can do. And since it's a very rare process, to consider many channels. So I will guide you through this. This is a grid. On the first column, it's the prompt case, because J psis can be produced either directly from the interaction or by a subsequent decay of a B hadron. So on this column, you see the single parton scattering on the first row, the double parton scattering on the second row, and triple parton scattering on the third row, the diagrams. And then on the 3x3 grid here on the right, you see the combinations of non-prompt. So now you start to introduce 1, 2, 3 non-prompts in the final state. And this is what you can see in the individual columns. So the first column on of this 3x3 grid is 2 prompt J size here on the top and 1 non-prompt that comes from a gluon splitting. Here you have 2 non-prompt J size and 1 prompt, and so forth. And by looking at it, you expect about 95% of the production to come from the 2 last rows, and only 5% from the top. And the specific diagrams that contribute the most are indicated by the red frame. So you expect double parton scattering and triple parton scattering to dominate, and the case where you have all combinations, 1 non-prompt, 2 non-prompt, or 3 non-prompt. So this is one of the events, how it looks like in the detector. It looks, at least for me that I'm working on this type of things, I really like muon final states, and I found this a spectacular achievement of the CMS to be able to do the reconstruction of this mode. And in our study, what we have done is, apart from the observation, we measured the fiducial cross-section and extracted the effective cross-section, the double parton scattering. So we used the run 2, so the data set that is being completed in 2018, meaning that since now we have in run 3 that is ongoing, actually it finished a couple of days ago, the PP for this year, we have surpassed the luminosity of run 2. It means that we can actually sort of double the statistics, or if with a bit more clever techniques, maybe 2.5, 3 times. We again really went very low in terms of PT and large in rapidity in order to scrape every single event. I'm not going to go through all the selections because it's again there for the slides to be complete. But the interesting thing is that we have 6 events. Out of the whole run 2 data set, we ended up with 6 events passing the selection criteria. 2 from 2017 and 4 from the 2018 data, 0 from 2016. And in order to check our efficiencies, we used Monte Carlo, and we had 2 sets of Monte Carlo samples. We used Helakone for that, and which is dedicated software that can do a lot of things around quark-Conning in general. We are using it in many Monte Carlo final state productions. So we didn't bother going through the SPS because it's very low yield that's expected. And we went ahead and with a double parton scattering and one of the dominant production mechanism, which is a mixture of double J psi, so J psi SPS and J psi SPS. So this is a double parton scattering. You have like one pair of partners giving you this final state and another pair of partners giving you this final state, and a triple parton scattering where each J psi is produced from a different interaction. So the distributions look like this, and performing an non-linear maximum likelihood fit, we got back 5 plus or minus of the order of 2, 3 events. So we have one background event, and I think it's pretty obvious where this one sits, unfortunately, for the 2 and for the 2 case. This is a mix. So in order to measure the fiducial cross-section, again we correct for efficiency, luminosity, and branching fraction now to the power of 3. Again, this is mainly for simplicity. The efficiency is very high because with muons, CMS is really highly efficient. And we ended up with a very low number on the systematic cross-section and a very high number on the statistical cross-section. So the measurement that we have is 270 femtobarns, plus or minus 100 and 140 statistical uncertainty, and 17 femtobarns systematic uncertainty. And again, this is a very, very rare process. And this is where the interesting part comes, again, the extraction of the sigma effective. So these were like a very small number of events. And the first thing that you have to do is classify them, right? You need to know which ones are prompt and which ones are not prompt. And in order to do that, we chose one approach and we validated with another. So what we did is that we placed a cut on the pseudo-proper decay length of the JSI at 16 microns. And then we said that whoever goes above it can be considered as non-prompt, the others as prompt. And we got this classification that we have 2 events in the 2 non-prompt, 1 prompt, 1 event in the 1 non-prompt and 2 prompt, and then 1 event in the 3 prompt and 1 event in the 3 non-prompt case. The cross-check was done by applying signal weights in the pseudo-proper lifetime distribution and fitting it. The result is the same. So we were confident that the classification is accurate. And then you need to start plugging in values. You start with a pocket formula so that the double partner scattering cross-section can be expressed as a function of single partner scattering cross-sections and the effective cross-section. And then you have also now the triple partner scattering, where you have the 3 times the single partner scattering and the triple partner scattering effective cross-section. But you need to go one step further, because now the total cross-section is the sum not only of single and double, but it's also as a function of triple. And then each one needs to be split as a sum of the promptness and non-promptness of each final state. So what you can do is that in the end you can derive and just go all the way down and follow the process down to individual components, which is the cross-section of the prompt and non-prompt cross-sections of J size or 2J size. So to derive a formula like the ones in the bottom. And to calculate each component, we used Helaconia, PTI8, and MADGRAPH5 at NLO. And this is the values for each one. So single partner scattering, single JSI production, of course, this is well understood in the level of 10%, a bit more in the case of the non-prompt. Then you have the double JSI production, which where the uncertainties become larger, as you can see here with respect to the single JSI case. Of course, the experimental input is a lot smaller, and the theory work. And in the end, the triple JSI production, there are some numbers which have more than 200% uncertainty. So it's a really has a really large uncertainty. In any case, if you let one parameter free, the effective cross-section float, and you replace the triple partner scattering effective cross-section with this formula, you can perform a fit on this value. And performing this fit of the classification of the events in the different categories and the double partner scattering, you get this event table where you return back that indeed the dominating process is here you have like 1.7 events and 1.7 events in the 1 prompt to non-prompt case and 3 non-prompt. And the second largest contribution comes from the triple partner scattering, where you have half of an event in the 2 prompt 1 non-prompt case and almost half of an event in the 1 prompt 2 non-prompt case. In total, 5. So this is the total number of events. This is the cross section that we measured. So this is what is being fitted. And this point sits like this. Again, it agrees in the window of 3 to 10 millibarns, where you would expect all these J-psi quarkonia measurements to lie. And calculating the contributions, we arrived very close to what we were expecting. So SPS is 6% with respect to 5% that we were expecting. DPS is 74, 75 we're expecting, and TPS 20. So this indeed is really the golden channel of studying double and triple parton scattering, especially with the datasets that are coming soon. And the effective cross-section is 2.7 plus 1.4 lower uncertainty 1, and 1.5 theoretical uncertainty, because we cannot constrain while the triple parton scattering mainly in double cross-sections. And here is again the comparison with the other measurements, now highlighting the bands where you would expect gluon-induced and quark-induced processes. So the conclusion for this analysis is that we observed for the first time the triple J-psi production and measured the fiducial cross-section, and we extracted the double parton scattering cross-section using this case. And the two analyses that I presented to you today are the two first ones that are sitting here on the quarkonia band. So I want to just finish with this summary and blame all to us experimentalists that we keep using this parameterization, that we fold everything under the effective cross-section, although we have a lot of data and we have a lot of processes and final states that we have not probed to a great detail still. So we can do many clever things, mainly to use as input to double parton scattering, to double parton distribution functions, and other models like the hot point model that was mentioned, and sort of revived some calculation and used sigma effective as input. So there is a lot of excitement ahead, I hope. Yes, that's it. Thank you.
Okay, thank you very much for the talk. So, questions?
Hi, Stefanos. Thank you. Very nice talk. I have some question about the value of the effective cross-section in the triple parton scattering. The CMS collaboration find the 2.7, but the LHCb finds at the same energy 30 millibar. Do you know the reason about this difference between two related measurements?
Yeah. I don't know. I can venture a guess with I think high probability, and it's hidden here. Actually, this is the source. So essentially, what we are doing is that we are folding this formula under the effective cross-section, but we know that the double parton functions here are behaving differently when you go to high rapidity and when you go to central rapidity. So when you go to high rapidity, there are correlations, interparton correlations, and the double parton distribution functions are way different. So the results I would expect not to agree to a good extent. And this is also the reason that we don't include in such plots the LHCb measurements, because it's in a different phase space.
Oh, okay. Thank you.
That's why I'm saying that we also do a bad job. We need to find some common knowledge and give to theorists some inputs so we can, merge ahead somewhere we can have a common ground.
Okay. And there are some model for the DPDFs that take account these correlations depending on rapidity, or?
Yeah, there is a lot of work. There is a lot of work from many colleagues, theory, that are developing. I've seen publications also for generalized double distribution functions that are very interesting. But I am not in a position to comment more than that. I'm super heavy on the experiment side to be able to make a very good assessment of that.
Okay. Thank you.
Sure,
Very
thank
nice
you.
talk.
Okay, I have one question. So you said that there will be no in the near future there will be no proton-lead run. Okay, so why did they decide that, and when do you think you're going to have another run?
Yeah, that's a good question. There was a workshop in summer trying to gather ideas and advocate that we need a PLED data set. And we're trying to write up something and push for it. But the next one is hopefully either the first or second year of the HLLHC running. So that means, I don't know, 2029 or 2030, something like that. Other colleagues suggest and say like, oh, why don't you go and do it in lead-lead collisions that you have? But there you can imagine that the situation is a lot worse because you don't have a projectile interacting, but you can have many combinations of interactions giving you 2J size, which is uncomprehendable. You cannot make anything out of it.
Yes, I have also a question about this slide. So when you measure the events, including the cuts, right? How many of the events were of the type 1, and how many of the events were type 2?
Good question. We cannot distinguish, unfortunately. We don't have the statistics to distinguish, and we are currently trying to see if we can generate some smart Monte Carlo to even say if we can distinguish the two, if there is some variable that can allow us to distinguish the two contributions. Because I mean, your comment is spot on. We can really even do a more detailed measurement of these components if we could. Yeah, it's work in progress.
I see. But do you have a percentage in mind that you expect?
In principle, this one is more abundant by 50%, I would say.
Okay. Okay, thank you. Any further questions? Mais alguma pergunta, pessoal? Se quiserem, eu posso traduzir para o inglês também a pergunta. Se quiserem digitar ali também, a gente lê a pergunta. Okay, so I guess... go ahead, please.
Are there in the CMS Academy future DPS measurements in the next run? Or
yeah, in principle, we are trying to do a lot of combinations of germanium with higher germanium states like LHCb published J psi with psi prime. We're also actively studying the double J psi because it's background on the tetraquark, which it's also needs to be very well understood. And there was some interesting, since we introduced these low, we introduced some low triggers, smart triggers that use very low PT muon and save only the muon information. And doing that, we could revive the triple J-psi and probe it with higher statistics. But it's to be seen. It's a bit early for that specific one. To be seen.
This will be good to comparison with the
Yeah.
CB measurement. Oh, great.
Yeah, indeed.
Okay, I guess that's it. Thank you very much. That was very enlightening. And
Thank you.
I hope you get some new measurements for us in the near future, okay?
Yeah, hope so too.
Yeah.
Hope so too.
Yeah.
Okay, bye-bye.
Bye.